Taylor's theorem. Well, thus far, we've been looking for Taylor series without actually concerning ourselves with convergence. So what I'd like to do is start with some function, write down its Taylor series around 0. Maybe I'll assume that this function is infinitely differentiable, so I can actually write down its Taylor series around 0. And I mean, it's probably too much to hope that these are equal, but at least, I could replace this infinity with some big number n, and maybe I can't hope for equality, but I could at least hope that my function is being approximated by this partial sum of its Taylor series. Taylor's theorem is a result that's going to let us pull that off. Well, here's a statement of Taylor's theorem, there's actually a lot of results that are called Taylor's theorem that are all sort of like this. This is kind of a weak result, and I'm just doing it around 0. But anyhow, okay, so Taylor's theorem. Here's a statement of Taylor's theorem. Suppose that I've got some function from the real numbers to the real numbers, and just to make this a little bit easy, I'm going to say it's a smooth function, so it's infinitely differentiable. And I've picked some number big N, and then I'm writing out f of x equals the big nth partial sum of its Taylor series around the point 0. And I'm saying that f of x is equal to this plus this error term, or what's usually called the remainder term, so big R for remainder. And of course, this is necessarily true. I mean, f of x is equal to anything plus some error, So the big deal here isn't that I can write f of x like this. It's that I know something about the error term. Here's the upshot. Then the error term, or the remainder term, is given by this formula. The big nth plus 1th derivative of f evaluated at some point z divided by big N plus 1 factorial times x to the big N plus 1, and this point z is just some point between x and 0. We'll eventually give a proof of Taylor's theorem, but in the meantime, let's just see how we can use Taylor's theorem. So we've already considered the Taylor series for sine x around the origin. It's the sum n goes from 0 to infinity of minus 1 to the n over 2n plus 1 factorial times x to the 2n plus 1. And what I want to show now, what the big goal is to show that sine x is actually equal to its Taylor series regardless of what x is. To get there, we're going to use Taylor's theorem to control that error term, or that remainder term. Just to make it a little bit easier to talk about this, let's have f of x equals sine x. Let me just write out then what Taylor's theorem is telling us. Taylor's theorem is telling us that sine x minus the big nth partial sum, so the sum little n goes from 0 to big N, of the Taylor series, which is the nth derivative of f at 0 divided by n factorial times x to the n. So I'm just writing out the Taylor series in general. This is this remainder term, big R sub n of x. And what Taylor's theorem tells us is that I've got a formula for this remainder term. I can control the remainder in terms of the big N plus 1th derivative of f. It's telling me that big R sub n of x is equal to f, the big N plus 1th derivative of f, at some point z divided by big N plus 1 factorial times x to the big N plus 1 power for some point z which is between 0 and x. But I know something about how big the big N plus 1th derivative of f is. Well, I don't know anything about big N, but I know that if I were to differentiate sine any number of times, it doesn't matter how many times I differentiate sine, I'm either getting plus or minus sine, or maybe I'm getting plus or minus cosine. But regardless of how many times I differentiate sine, I'm getting one or the other of these things, maybe with a plus or a minus sign. And what that means is that regardless of what big N plus 1 is, the absolute value of the big N plus 1th derivative of sine at some point x can be no bigger than 1 in absolute value. So I can use this knowledge to say something about the remainder. Because this is true about the big N plus 1th derivative of f being no bigger than 1, that tells me that at least in absolute value, the remainder is no bigger than, well, how big could this be in absolute values? 1. So it's no bigger than 1 over n plus 1 factorial times x to the n plus 1th power in absolute value. So I'd like that to be small, or even better, I'd like to say something about the limit. So fix some value of x. I don't need to consider varying values of x. I just want to consider a fixed value of x. And I want to show that this is small in the limit. I want to show that the limit as big N goes to infinity of the absolute value of x to the big N plus 1th power over big N plus 1 factorial. I'd like to show that the limit of this is 0. Why would thinking about the limit be a good idea? Well, if I know the limit of this is 0, then I know that another limit vanishes. Then I know the limit as big N approaches infinity of something that's smaller than this, something closer to 0. Well, here's something, right? Then I know that the limit of the remainder term is also equal to 0, because this is bigger than this. But why would I care about knowing the limit of the remainder term is 0? Well, remember what this is measuring, right? Big R is measuring the distance between the function and the big nth partial sum of its Taylor series around 0. So if I know that in the limit as big N approaches infinity, this goes to 0, that means in the limit this goes to this. But what's the limit of this as big N goes to infinity? Well, let me write that down, right? What I'm saying is that sine of x then must be equal to the sum n goes from 0, and I'd write the big N here, but I'm taking the limit as big N goes to infinity. And that's exactly what this series notation means, right? So what I'm saying is that if the remainder goes to 0 in the limit, then sine is actually equal to its Taylor series around 0, right? That means that sine of x is actually equal to its Taylor series. And I know another way of writing down the Taylor series, right? Then I can say that sine of x is actually equal to the sum n goes from 0 to infinity. And instead of writing down this, where I haven't actually described what these coefficients are, I could write down minus 1 to the n over 2n plus 1 factorial times x to the 2n plus 1. Because we've already seen that if we differentiate sine a bunch of times, this is exactly what we get here. So that is a great goal. Right, so I've got to figure out some way to show that this limit is 0. Well, how do I deal with that limit? Well, there's a trick. Claim the sum, big N goes from 0 to infinity, of the absolute value of x to the big N plus 1 over big N plus 1 factorial converges. If I can show that this series converges, then I know that the limit of this is equal to 0. But how do I know that that series converges? Well, let's use the ratio test. So I should look at the limit as big N goes to infinity. It seems like it's going to be worse, but it's going to be better. Of the n plus 1th term here, where n is replaced by n plus 1, divided by this term here. So let me write that out. It's going to be the limit of x to the big N plus 2 divided by big N plus 2 factorial. And that's divided by x to the big N plus 1 over big N plus 1 factorial, taking absolute value of this. Now, how do I evaluate this limit? I mean, this maybe seems worse, but there's a lot of fortuitous cancellation. So this limit ends up being the limit as big N approaches infinity. Well, I've got an x to the big N plus 2 divided by x to the big N plus 1. So this is just x, just one copy of x survives. Here, I've got an n plus 1 factorial in the denominator of the denominator. So I'm just going to move that up to the numerator. So I've got n plus 1 factorial in the numerator. And then in the denominator of the numerator, I've got n plus 2 factorial. I'll just put that in the denominator. Okay, so I've got to calculate this limit. But now what's this limit? Well, I've got an n plus 1 factorial in the numerator and an n plus 2 factorial in the denominator. So this is the limit as n approaches infinity of x over just n plus 2. And what happens now? X is fixed, big N is approaching infinity, so this limit is equal to 0. 0 is less than 1, so by the ratio test, this series converges, and therefore by the nth term test, if you like, because the series converges, that means that this limit is equal to 0. Let's put it all together. So really, the argument starts when I fix some value for x. I just pick a single value of x, and I'm going to consider just that value of x from now on. Now what happens? I fix that value of x, and for a fixed value of x, the limit as big N approaches infinity of that fixed value of x, just a constant as far as big N is concerned, divided by some number that's going to be enormous. This is 0. But this is also calculating the limit of the ratio between subsequent terms in this series. That means by the ratio test, since this limit is 0 and 0 is less than 1, which is the cutoff for the ratio test, that means that this series converges. Now because that series converges, that means the limit of its nth term must be 0. But because that limit is 0, I know something now about the remainder, right? The remainder is bounded above by this term. So if this limit is 0, that tells me something about the remainder. It's telling me that the limit of the remainder as big N goes to infinity is equal to 0. But if the remainder term is going to 0 in the limit, right, that tells me that the difference between sine and its big Nth partial sum is going to 0 as big N goes to infinity. But that's just to say that sine of x is actually equal to its Taylor series, because the error between sine of x and the big Nth partial sum over here is going to 0. So in the limit, right, when big N is going to infinity, sine of x must actually be equal to its Taylor series. We've already found its Taylor series. Here it is. And this is true for all real x, because at the beginning of this argument, I just picked one value of x, but I didn't use anything about that value of x. So this must be true regardless of what x is. That is truly a triumph. This is a huge success. This very mysterious function sine turns out to be given everywhere by this relatively nice looking power series.